This module is about selecting and sizing pumps for irrigation systems. With so many different kinds of pumps and so much technical information to sort through, this can feel like a mysterious and overwhelming task. But don't worry, figuring out which pump you need isn't rocket science. The goal of this module is to demystify the process and will give you the tools you need to be able to confidently select the best pump for any irrigation system. In any introduction to irrigation design, installation, or service, you learn that there are two hydraulic measurements that matter: the flow rate in gallons per minute, or GPM, and the water pressure in pounds per square inch, or PSI. Pipe size, sprinkler type and nozzles, zone size, and even the layout and arrangement of pipe underground depends on these two things. Whether you're designing or installing a system, all of the decisions you make are directed towards two goals. 1. Making sure that there is enough flow, GPM, to feed the largest zone, and 2. Making sure that there is enough pressure, PSI, at the sprinkler at the end of the run with the greatest pressure loss. If you're servicing an irrigation system, you know that if there's a problem with the sprinkler, apart from a broken or defective sprinkler head, there's either not enough flow to the sprinkler head or there's not enough pressure at the sprinkler to make it operate correctly. Pressure and flow. These are the two things that matter in an irrigation system. And it is these two things more than anything else that dictate the choice of a pump for the irrigation system. All of the other things that people talk about when they're talking about pumps, horsepower, voltage, impeller, and motor size, centrifugal or submersible, all of these things are in the service of creating enough flow for the largest zone and enough pressure to power every sprinkler head in the system. One of the great things about using pumps is that you can change the flow and or the pressure of the system. An irrigation system with a pump isn't like one hooked up to city water, where the pressure and flow rate are determined by the city water supply at your location. You have the flexibility to tailor the water supply to your system's needs, either by increasing the pressure or, if using a well, lake, or pond, by increasing the flow rate of the system as well. In any case, the most important things you'll need to know when selecting and sizing the pump are your desired pressure and flow rate at the point the water leaves the pump. We'll go into specifics of how to calculate those things later on in the module, but for now, we're going to take a moment to talk about the other things you'll need to know so that you can select the right pump for your situation to meet the flow and pressure needs of the system. Out of the plethora of pump options listed in a typical pump catalog, there are relatively few that are used in irrigation systems. Before going into specifics, let's take a brief moment to talk about the different kinds of pumps used in irrigation applications. All irrigation pumps have three main components: a motor that drives the pump, an impeller that spins around, pushing water from the inlet at the center of the impeller away from it, and a diffuser, which is a casing around the impeller that collects the moving water and moves it to the outlet. These components are arranged in two main ways. The first kind of pump is submersible. In submersible pumps, both the motor and the impeller are placed below the water. The motor spins the impeller, or impellers, in the diffuser, and this forces water up a pipe and into the irrigation system. The second kind of pump is a centrifugal pump. With the centrifugal pumps, the pump is located on dry land, and water enters the pump through a pipe and is pumped from there out to the irrigation system. You'll see centrifugal pumps referred to by different names, including booster pumps, high head pumps, and suction lift pumps, among others. They're all varieties of centrifugal pumps, but are engineered differently to meet the needs of different situations. Jet pumps are centrifugal pumps fitted with a jet and a venturi to allow the pump to lift water from greater depths. In order to choose the right type of pump, you'll need to know what and where your water source is. If your water source is a well, the most common type of pump used is a submersible pump. A well is created by drilling a hole into the ground that reaches below the water table. This is lined with pipe, and at the bottom of the well there is water available to be pumped out. For deep well situations, a submersible pump is lowered down the pipe and submerged into the water at the bottom of the well, where it pushes water to the surface and into the irrigation system. For areas with high water tables, you can use a centrifugal or centrifugal jet pump instead. The jet in a jet pump allows the pump to be mounted higher above the water level than a standard centrifugal pump. Shallow well jet pumps can be used in water sources up to 25 feet deep. Deep well jet pumps can be used in a water source up to 110 feet deep. In these situations, instead of lowering the pump itself into the well, the intake pipe is run to the bottom of the well and it uses suction created by the pump to lift water out of the well and then push it into the irrigation system. There are limitations to the height that can be overcome through the suction lift mechanism, which is why submersible pumps, where the pump is below the water level, are required for wells deeper than 110 feet. So for wells, you have three options.
If the water source is under 25 feet deep, you can use a centrifugal or shallow well jet pump. For water sources between 25 and 110 feet deep, you can use a deep well jet pump. For water sources deeper than 110 feet, you will have to use a submersible pump.
When pumping water out of a freshwater source like a lake, pond, or stream, the most common pump choice is a centrifugal pump. Because there is usually a shorter vertical distance between the water level and the pump, you don't need a jet to get the water into the pump. The force exerted by the air pressure on the water is enough to push the water up to the pump. For situations in which there is a significant elevation change between the water level and the pump, or where there is no suitable place to put the centrifugal pump, a submersible pump is sometimes the better choice. We'll talk more about how the elevation change affects pump choice a little later on. If your irrigation system is connected to a municipal water system, the best pump for the situation is a centrifugal pump, because the water coming into the pump is pressurized. These pumps are only adding to the water pressure, so you can get away with a smaller centrifugal pump than would be required if the pump was providing all of the pressure. Most manufacturers carry a line of smaller pumps called booster pumps for this purpose. It's important to recognize that a booster pump can't change the amount of flow available in the irrigation system. This is determined by the size of the water meter, and it's fixed, unless a larger meter can be installed. A booster pump can only boost the pressure of the system, which is where it gets its name. Once you have an idea about what kind of pump you'll need for your irrigation system, there are a few additional details you'll want to have at hand in order to make your selection: the power supply, pump location, and water quality. All pumps require power, and the bigger the pump, the more power it needs. While a small booster pump may only need a regular 110-volt outlet to plug into, larger pumps require a 220-volt or larger connection. Pumps are also designed to work with either single-phase or three-phase power. Three-phase power isn't available at all locations, but where it is available, the pump uses electricity more efficiently, requiring smaller wires than the same-sized pump running on single-phase power. Three-phase power is recommended for pumps over 5 horsepower. So, before you order your pump, you'll need to know the voltage options that you have available, as well as whether the power is single-phase or three-phase. If there is no power located where you want to place your pump, or you don't have a dedicated outlet or connection point available, you may need to arrange with an electrician to have power run to that location. The location of the pump is also something to consider when making your selection. A centrifugal pump will require a mounting pad and pump shelter if it is installed outdoors. If there isn't any place to put this, or if these structures are undesirable, you may consider choosing a submersible pump, even if a centrifugal pump will work for the application. The final detail to consider is water quality, especially if you're pumping from a lake, pond, or stream. While this won't necessarily affect the choice of pump, it may require you to include intake or post-pump filtration, which could factor into your system calculations. That would be great to be able to walk into your distributor's location, tell them you want a sprinkler pump, and walk out with the right pump for the job. Unfortunately, it's a bit more complicated. And if you do buy something called a sprinkler pump, beware. It may be designed to power just one sprinkler. Let's take a moment to review the considerations you'll need to make in order to choose the right pump. The objective of a pump in an irrigation system is to ensure that there is adequate flow, GPM, for the largest zone and sufficient pressure, PSI, to reach the sprinkler head with the greatest pressure loss. There are 2 criteria used to size a pump. Because these criteria help you determine what size of pump you need, which is expressed in horsepower, many people think that all pumps with equal horsepower are the same, but they're not. Different pump configurations with the same horsepower will produce different combinations of flow and pressure. So don't assume that a 2 horsepower submersible pump, for instance, is the same as a 2 horsepower centrifugal pump, or even that 2 centrifugal pumps with the same horsepower are the same. You'll have to check the performance of each pump to ensure you're getting the right pump for your system. With these 2 criteria firmly in mind, you'll also need to consider your water source, power, location, and water quality to arrive at the right pump for the job. In review, For wells, submersible pumps are the most common choice for deep wells, while jet pumps can be used for shallower wells. For lakes, ponds, streams, and other bodies of water, centrifugal pumps are the most common solution, although submersible pumps may also be used. For municipal water systems, centrifugal booster pumps will boost pressure to the desired level, but cannot change the available flow rate. Other things to note are what kind of power, voltage, and phase is available, where the pump will be located, and what kind of pump will work in that location. Whether water quality will require filtration that will affect the needed pressure. There is no one-size-fits-all pump. The reason that selecting and sizing a pump is so important is because each irrigation situation is just a little different, and you have to take into account the particulars of the situation to ensure that you select the proper pump for the job. Before we go any further, let's take a minute to understand pump terminology. There are a number of terms that are essential to understand when selecting and sizing a pump, and they're all related to the two basic needs of the system: flow and pressure. As you know, these two needs are independent. In an irrigation system, you can increase the flow rate without increasing the pressure, and you can increase the pressure without increasing the flow rate. They are two distinct measurements, and you need to know how much each of your system needs to operate. The measure of flow rate is gallons per minute. This measures the quantity of water moving through the system during a specified amount of time. The critical thing to know is how many gallons per minute are used by the largest zone of the system, or the maximum number of gallons per minute that the system will use at any one time if you plan on running more than one zone at a time. If that's 15 gallons per minute, you know that in 1 minute's time, 15 gallons have gone through the system, and 15 gallons have flowed out through the sprinklers. There are a number of terms that we use to talk about pressure which enter into the calculations used to select a pump for the system. Pounds per square inch, or PSI, and feet of head are both units measuring pressure. Suction lift, elevation, and friction loss are all forces that affect the pressure of the system. Let's have a look at how these are related. Pressure is a measure of the amount of force exerted on the water in the system, pushing the water through the system and, when the sprinklers are activated, through the sprinklers and out into the landscape. There are a number of ways to measure it, but the two most commonly used in irrigation when sizing pumps are pounds per square inch and feet of head. It may sound like these two quantifications of pressure are wholly unrelated. One's in pounds, the other's in feet, am I right? But they're actually very closely related. The unit pounds per square inch is a measurement of weight, and in particular, a measurement of weight applied to the surface of a specific size. The weight is expressed in pounds, and the surface size is 1 square inch. So if you put water into a pipe that has 1 square inch and placed a 1 pound weight on top of it, the amount of pressure on the water in the pipe will be 1 pound per square inch. The unit feet of head is based on the weight of water. 1 foot of head is equal to the amount of weight that 1 foot of water places on 1 square inch of surface area. So if we took our 1 square inch pipe that was filled with water, and instead of putting a weight on it that we measure in pounds, we poured in 1 foot of water, that water would push on the surface of the water originally in the tank with all of its weight. And it happens that 1 foot of water standing on top of 1 square inch area weighs 0.433 pounds. So when we're talking about pounds per square inch or feet of head, we're actually talking about the same thing: the amount of weight that's pressing on the water in the pipe at any given time. One measurement is based on the familiar unit of pounds, and the other is based on the weight of a column of water. We use both of them because sometimes it's easier to calculate feet of head, and sometimes it's easier to calculate pounds per square inch. When we go to make our calculations, we just have to convert one unit to the other, which we can based on the weight of water. Because a 1 foot tall column of water, 1 square inch, weighs 0.433 pounds, we know that 1 foot of head equals 0.433 pounds per square inch. We can convert the other way as well. We can divide 1 pound by the weight of a 1 inch square column of water that's 1 foot tall to determine that 1 pound is equal to a 2.31 foot column of water. So 1 pound per square inch equals 2.31 feet of head. The really slick thing about using feet of head is that if we know the vertical distance between 2 points in the irrigation system in feet, that distance is equal to the difference in pressure between those 2 points, expressed in feet of head. Let's consider a very basic example of how we might use these two measurements of pressure to understand the water in an irrigation system. To keep things incredibly simple, suppose there is a water tower connected directly to a sprinkler system with one sprinkler at the end of it, and we want to know how much water pressure there is at the sprinkler head. Suppose we measure 35 feet between the water level in the tower and the base of the tower on the ground. To figure out how much pressure this is putting on the water at the beginning of the irrigation system, we'll use feet of head, because that's really easy to calculate. If water level is 35 feet tall, there are 35 feet of head of pressure at the starting point of the irrigation system. Now, as the water moves through the pipe headed towards the sprinkler, it creates friction with the walls of the pipe, and this reduces the pressure at the end of the pipe run. We call this friction loss. We can figure out what the friction loss in our pipe run will be by looking at a chart that estimates friction loss. Let's suppose that there's 300 feet of 1-inch SDR21 or Class 200 PVC pipe between the water tower and the sprinkler head, and that the sprinkler head uses 10 gallons per minute of water. It's a big sprinkler. Consulting a friction loss chart, we can see that the water will experience a loss of 1.30 psi for every 100 feet of pipe. Since we have 300 feet of pipe, we can multiply this by 3 to determine that we will lose 3.90 psi by the time it gets to the sprinkler. Now we know all that we need to know to calculate the pressure at the sprinkler. It will be equal to the pressure at the beginning of the sprinkler system minus the pressure lost between the start of the system and the sprinkler. We can calculate it in either terms of PSI or feet of head, but in this example we'll use PSI. To convert the feet of head to PSI, we multiply 35 times 0.433 to get 15.15 PSI at the beginning of the irrigation system. So the total pressure at the sprinkler head will be 15.15 PSI minus 3.90 PSI, which equals 11.25 PSI. Now this example was an easy one, but it uses all of the concepts you'll need for the calculations to properly size a pump. There are two additional terms that come up when sizing a pump: elevation and suction lift. Unlike friction loss, it's easiest to calculate these in feet of head. Elevation is the vertical distance between the pump and the highest point in the irrigation system. The number of feet of vertical distance is the feet of head of pressure difference between those 2 points. Suction lift is the vertical distance between the pump and the water source it is drawing from, and it is used when sizing a centrifugal pump drawing from a well, lake, pond, stream, or other body of water. To convert these to PSI, just multiply the number of feet of head by 0.433. Woo doggy, now we come to the exciting part, actually sizing a pump for an irrigation system. Let's start out with a checklist of what you'll need to know in order to begin. First, you'll want to have a sense of what kind of pump you're looking for. You can use the considerations discussed in Part 1 to get started. Based on your water source, determine which kind or kinds of pumps will be the best fit for your needs. Centrifugal pump, jet, suction lift, or booster. What kind of power is available? 120 and or 220 volt, single and or three-phase? Is there a place to mount the pump, or does the location require a submersible? Will the water quality require filtration? Next, we'll need to calculate the two crucial numbers for correctly sizing the pump: the flow rate and the pressure. This is what you'll need to know to calculate these. For the flow rate, you'll need to know the flow rate in GPM of the largest zone in the system, or if more than one zone will be running at a time, the maximum flow rate that the system will use at any one time. For the pressure, you'll need to know the pressure that's needed at the sprinklers to operate the system. For a quick reference, in a residential system, rotors typically require 50 psi, rotary nozzled sprinklers typically require 40 psi, fixed sprays typically require 30 psi. Drip irrigation zones usually require 30 psi as well. On high pressure systems, a pressure reducer is used to pressure down. You'll need to know the friction loss between the location of the pump and the sprinkler with the greatest pressure loss. This includes things like changes in elevation between the pump and the highest point in the irrigation system, and friction loss encountered in pipes, fittings, and valves. Finally, you'll need to know about the water pressure or elevation of the water coming into the pump. This can be one of two different things: the pressure coming into the system, if it is connected to the city water, the height of the pump above the water level of a well or body of water, which is called suction lift. Let's tackle each of these items in turn, looking at an example. Suppose we're selecting a pump for the irrigation system at a lovely lake house, as pictured here. Rather quaint, isn't it? Now there's quite a bit of elevation change over this property, as you can see by the side view. The property rises 4 feet off the lake, then levels off, where we see the deck in the diagram, before rising an additional 8 feet to the street level where the property abuts the road. The first thing we'll do is calculate the required flow. To do this, we need to find the zone on the system that has the highest flow rate. This system has a mix of heads, with sprays, rotary nozzles, rotors, and drip irrigation. Finding the largest zone isn't just a matter of finding the zone with the largest number of heads. You have to add up the flow rates of each head to arrive at the flow rate for the zone. We can see that Zone 1 has 4 rotors sized at 1 GPM and 1 at 4 GPM, for a total of 8 GPM. Zone 2 has 6 fixed sprays totaling 9.2 GPM. Zone 3 has 4 rotors totaling 12 GPM. Zone 4 has 3 rotors totaling 8 GPM. And Zone 5 has 10 rotary nozzles totaling 4.5 GPM. Zone 5, with the rotary nozzles, looks like the biggest zone in the system when counting sprinkler heads, but it's actually the smallest zone in the system by flow rate. For this property, we'll base our flow rate on Zone 3, which uses 12 gallons per minute. So, the required flow rate for this system is 12 GPM. The required pressure at the sprinkler head is based on the sprinkler type. And in our system, we have the most common types of residential sprinklers. The rotors in Zones 1, 3, and 4 require 50 psi. The rotary nozzles in Zone 5 require 40 psi. And the fixed sprays in Zone 2 require 30 psi. To be sure our system can handle all three, we'll select 50 psi as the required pressure for the system. So the required pressure at the sprinkler head is 50 psi. Water moving through the system will create friction with all of the components of the plumbing between the pump and the last sprinkler on the line. The pressure loss caused by this friction can be estimated using friction loss charts for each component. The 3 sources of friction loss you'll need to consider are the pipe, fittings, and valves. To properly measure the friction loss, you'll need to know the size of pipe, type of pipe, and fittings, and length of pipe. The way that friction loss is measured with the fittings and valves is in equivalent feet in pipe. So for each fitting and valve, we add a certain number of feet of pipe to the total length of pipe that we're using. The system has been installed with 1-inch SDR21 PVC pipe and uses 1-inch fittings and valves. The first thing we need to do is count the number of fittings and valves. We'll base our count on the sprinkler farthest from the pump in Zone 5. To reach that sprinkler, the water will have to travel through 1 valve, 2 elbows, and 3 T's. Consulting the chart, we see that we need to add 3 feet for every elbow, 6 feet for every side outlet T, and 4 feet for the valve. This adds up to 4 plus 2 times 3 plus 3 times 6, 28 total feet of 1-inch pipe. We'll need to add this to the total length of pipe between the pump and the last sprinkler in the zone, so we'll need to measure the total length of main line plus the total length of pipe in the zone to reach the last sprinkler on the line. In this example, let's say that's 200 feet of main line plus 200 feet of zone line. Add the additional 28 feet to account for the friction loss in the fittings and valves, and we have a total of 428 feet of pipe. With our maximum flow rate of 12 GPM, we can consult the pressure loss chart to determine that the pressure loss will be 1.83 psi per 100 feet of pipe. To get the total pressure loss over the 428 feet of pipe, we multiply 1.83 times 4.28 to get 7.8 psi. Therefore, the friction loss in the system is 7.8 psi. In our example with the water tower, the elevation of the water in the tower created pressure. But if there are sprinklers in the irrigation system that are higher than the pump, the change in elevation will reduce pressure. Once again, the measurement is pretty straightforward. When calculating elevation, you only measure the vertical distance. If we take a look at the side view of the property, we can see that the sprinklers in the front yard are 8 feet higher than the pump, which adds 8 feet of head to the total amount of pressure lost by the time the water reaches the final sprinkler. To convert this to PSI, we simply multiply 0.433 to get 3.46 PSI. So the elevation causes a loss of 3.5 PSI. Suction lift is the distance between the level of the water source and the pump. When drawing from a lake, pond, stream, or other body of water, the intake of the pump will be located below the water level and fed up to the pump. The suction lift of the pump is the distance between the water level and the pump. In a well, the intake pipe is lowered into the well below the level of water table. Once again, the suction lift is the distance between the level of the water table and the intake of the pump. Suction lift is created when the pump creates a vacuum in the intake line, and the air pressure forces the water up into the pipe and into the pump. There's a limit to how high the air pressure can push the pump, 25 feet. If the suction lift is greater than 25 feet, you'll need a jet pump or a submersible pump to move the water from the water source into the irrigation system. In our example, there are 4 feet of suction lift required to reach the pump, which when multiplied by 0.433 equals 1.7 psi. Thus, the suction lift requires 1.7 psi. Okay, now we know all of the things we need to know in order to size the pump, so let's gather it together to get the 2 numbers we need to know: the required pressure and flow rate. To get the required pressure, add up the following: required pressure at the sprinkler head, plus friction loss, plus elevation change, plus suction lift. So in our example, this will be 50 plus 7.8 plus 3.5 plus 1.7, which equals 63 psi. So the total pressure required is 63 psi. We also know the flow rate required is 12 GPM. Now, we're not all math geniuses here, so oftentimes it's easy to get numbers mixed up or to forget what an exact formula is. Here's an alternative method called the house of resistance model you can use that may help keep all the information and numbers clear. Think of it as building a house equals size of a pump. The house of resistance is not a large house. It only has 4 rooms. Each room houses the measurement for pressure, lift, elevation, and friction. Everything you'll need to calculate the PSI required. The chimney holds the GPM for the peak flow rate. It's easy. Simply fill in the rooms with the measurements. Most homes are measured in square feet. And in the house of resistance, we also show measurements in feet in every room of the house. Let's walk through our example. The first room is required pressure at the sprinkler head. We know that the required pressure is 50 psi for the largest zone. To convert this into feet, we'll multiply it by 2.31 to get 115.5. It is totally acceptable to round this number to 116. Next, we'll fill in the elevation change. In our example, we know that the sprinklers in the front yard are 8 feet higher than the pump, so we'll simply put 8 in the second room. Since we know there are 4 feet of suction lift required to reach the pump, we'll put 4 in the third room. And we've already done the math to know that the friction loss in our example was 7.8 psi. To convert this to feet, we'll multiply it by 2.31 to get 18.018, which we're going to round to 18. If you prefer, you can also use a friction loss chart to go straight from GPM and size of the pipe to friction loss in feet of head. Either way, you get the same result. The final step is to add up all 4 rooms of the house to arrive upon the total feet of head required. In our example, it is 146 feet. Now we're ready to select the right pump for our situation. Most pump manufacturers offer a few models of pumps that serve a wide range of irrigation applications. Flint & Walling, for instance, offers a line of irrigation workhorses under the CJ101 series. When selecting a pump, you'll use a pump curve to find the correct pump size for your flow and pressure needs. Let's take a look at the pump curves for the CJ101 series to find the proper size for our situation. There are a couple things to notice about this curve. First, you'll see that the vertical axis measures pressure, and it gives the pressure in both PSI and feet of head. And the horizontal axis measures flow rate in GPM. We're going to be looking at the point where our required pressure meets our required flow, and select the pump curve that contains that point. In this curve, our flow rate and pressure requirements intersect here. You'll notice that it doesn't matter if we use the total PSI required or the total feet of head required. Our intersecting point will be in the same spot. Either method you use places it on the right curve for the 2 horsepower 2-stage pump. This point is outside of the capacity of the smaller pumps, and the larger pumps are designed for much greater capacity. This then is the pump we're looking for. You'll notice that this point falls in the middle area of the curve, which is the highest efficiency area for the pump. Sometimes it's called the sweet spot. Pumps operate best in this area, somewhere in the middle of their range, so it's best not to select a pump where your requirements fall on the outside edges of the pump's capacity. More times than not, you'll find that your intersecting point on the pump curve falls between 2 pump selections. If we had a job that required 25 GPM and 150 feet of head, our intersecting point would land here. look at the pump curve directly to the left of the target orange circle. If you select this pump, follow its line until it intersects with 150 feet. Going straight down from where the line meets 150 feet, you'll notice that this pump would deliver approximately 15 GPM, which is far short of the 25 GPM required. Look at the pump curve directly to the right of the target orange circle. If you select this pump, follow its line until it intersects with 150 feet. Going straight down from where the line meets 150 feet, you'll notice that this pump would deliver approximately 30 GPM, which is more than adequate to meet the 25 GPM peak demand. That is the correct selection of pump. Once we know this, you're ready to place your order. Provide the distributor with the model number, here a CJ101, horsepower, and number of stages, if that's an option. Here, 2 horsepower, 2 stage, and what kind of power supply you need. This model is available in 110 and 220 volt models with single phase or 3-phase power. If, instead of choosing a centrifugal pump, we opt for a submersible, the process for sizing the pump is the same. Though it's worth pointing out the submersible pump has 2 components, a motor and a set of impellers. Depending on the arrangement of the impellers, the pump will have different characteristics. So a 1 horsepower motor with a 5 GPM impeller package will produce 129 psi at 5 GPM in its sweet spot, while a 1 horsepower motor with a 15 GPM impeller package will produce 95 psi at 15 GPM in its sweet spot. The motor size is the same, but the performances are very different. For this application, we'll look at the Flint & Walling 4F series in the 15 GPM model. We simply locate the point where our flow rate and pressure requirements meet, and select the pump curve that contains them. Here, we can see that the point falls just outside of the half horsepower model curve, and well within the capacity of the 3/4 horsepower model. Selecting a pump boils down to knowing what kind of pump you need, and then knowing the pressure and flow requirements for the system. Once you know these things, selecting a pump is easy. To review, here are the steps to successfully select and size a pump. Identify the type of pump, submersible, centrifugal, jet, that's right for your water source. Note the power that's available, 120 or 220 volt, single phase or 3-phase. Plan for filtration based on water quality. Get the numbers you need to know. Flow, the maximum flow rate for the system in GPM. Pressure, the pressure required by the sprinklers, the elevation of the system at its highest point, the friction loss through the pipe, fittings, and valves, the suction lift of the pump. To size the pump, simply add the pressure requirements together and then use the pressure and flow rate to locate your needs on a pump curve. Then select the curve that contains your point and you're ready to order your pump.